Linear functions and models. A linear function is any function of the form f of x equals ax plus b. The graph of a linear function is a line, and we know that the slope of the line is a and the y-intercept is b. We already know this. The only difference here is that we are calling the slope a, which is a little bit different from normal. Usually we call it m. So in our first example here, determine whether the given function is linear. If it is linear, express the function in the form f of x equals ax plus b. So this first one here obviously is linear. The only thing we need to do to express it in the same form is to just switch around the two terms and say that it's 3x plus 2. In part B, is this linear? Well, g of x is equal to, if you multiply this out, we have 3 minus 6x, and we can rewrite this as negative 6x plus 3. So yes, that one is also linear. In part C here, we have h of x is equal to 4x plus 3x squared. And this is clearly not linear, right? Because linear functions do not have an x squared term. And finally, in part D, we have k of x is equal to 1 minus 5x over 4. This can be rewritten as 1/4 minus 5/4 x, which can also be rewritten as negative 5/4 x plus 1/4. And so, yes, this one is a linear function. So in the end here, this one is a linear function, this one, and this one is not a linear function. Graphing linear functions is something that we already know how to do. So let f be the linear function defined by f of x equals 3x plus 2. To graph this, we don't even need to make a table. We know that the y-intercept is 2. That means it hits the y-axis at 2. And the slope is equal to 3. And 3 is the same as 3 over 1, which means from this point, we can go up 3 to the right 1. And then we could put another point. And all we need to graph a line is 2 points. And for the second part, what is the slope of this graph? Well, the slope is 3 over 1. Slope and rate of change. For the linear function f of x equals ax plus b, the slope and the rate of change are both equal to a, and a is the coefficient of x. So it's important that we recognize that the slope is something that we call the rate of change. And so that tells us how fast the function values are changing with respect to how fast the x variable is changing. So as an example, a dam is built on a river to create a reservoir. The water level, f of t, in the reservoir at time t is given by the function f of t equals 4.5 times t plus 28, where t is the number of years since the dam was constructed, and f of t is measured in feet. So first, we want to just sketch the graph of this function. So again, we know that the y-intercept is 28, and so the y-intercept here is 28. So you can see that that is hitting the y-axis at 28. And then the way we get another point on the curve here is we use the slope. So if the slope is 4.5, keep in mind that this is 4.5 over 1. So what that means is for every 1 year that goes by, the water level is going to raise 4.5 feet. So after 1 year, we're going to add 4.5 to this number, which takes us to this new number here. After another year, So after another year that goes by here, we're going to add 4.5 again. So the slope of the graph is 4.5. And at what rate is the water level in the reservoir changing? Well, again, remember, that's the rate of change. And the rate of change is the slope of the graph. So the rate of change is 4.5. And this is going to be feet per year. So remember, the rate of change is typically going to have units attached to it. In this case, it represents how many feet that the reservoir rises in terms of the water level per each year that passes by. So now again, understanding slope as rate of change. Suppose we were looking at a container that has a volume of gas. So in this first part, we can see that when time equals 0, there is no volume in the container. And as time goes by, the volume is increasing, right? It's going up. And you can see that if you pick a couple of points on this line, in 3 minutes, it has gone up 6 gallons. So the rate of change is 6 gallons for every 3 minutes. And if you divide this, this is going to be 2 gallons per minute. Now, once this container is full of gas, and you can see that it's up here at 18 gallons now, then we start using the gas from the container, and you can see that the volume starts to drop. And it's dropping at a constant rate of change because we have a straight line here. If you pick a couple of points on this line, you can see that in 100 minutes, it dropped 3 gallons. So the slope here is -3 gallons per 100 minutes. And if you simplify this, this is -0.03 gallons per minute. So again, the slope represents the rate of change of this variable, the vertical variable, compared to the horizontal variable. Next, let's make a linear model. Suppose water is being pumped into a swimming pool at the rate of 5 gallons per minute. Initially, the pool contains 200 gallons of water. Find a linear function v stands for volume, that models the volume of water in the pool at any time t. Okay, so we know that the slope is going to be 5 gallons per minute, right? Because the slope represents the rate of change. And initially, the pool contains 200 gallons of water. So the volume is going to be 5 times t plus 200. So again, the slope is 5, and the initial quantity is simply the y-intercept, right? Because if t equals 0, which represents the beginning, we know the volume is supposed to be 200. Now for the second part, it says, if the pool has a capacity of 600 gallons, how long does it take to completely fill the pool? So for the second part, they're basically asking, when is the volume going to equal 600? So since I have my model here, all I need to do is plug 600 in for the volume. And if we do that, we can solve by subtracting 200 from both sides. And then we can divide both sides by 5. And when we divide by 5, we're going to get 80. So how long does it take to completely fill the pool? Well, it's going to be 80 minutes. In the next example, we have a staircase, And you can see that the origin corresponds to the bottom left of the staircase. And the red line is the edge of the trim board of the staircase. So the red line essentially touches the tops of all the stairs. Find a linear function h that models the height of the trim board above the floor. So again, h is going to be equal to the slope multiplied by x, because the independent variable here is x, and then plus the y-intercept. Well, you can see that the y-intercept is 8, so we just need to figure out what is the slope. Well, to get the slope, we have a couple of points here. We can just use the slope formula. So 32 minus 16 divided by 36 minus 12. And this is going to be 16 divided by 24. And this reduces to 2/3. So the function is going to be h equals 2/3 times x plus 8. For the second part, if the space available to build the staircase is 11 feet wide, so talking about 11 feet wide this way, how high does the staircase reach? So x is going to be 11 feet. Now let's keep in mind that if you look at the x-axis here, this is measured in inches. So we have to convert 11 feet into inches. So we need to do 11 times 12, right? Because there's 12 inches in a foot. And this is going to be 132 inches. And now we want to know, what is the height of the staircase going to be at 132 inches? So we just plug in 132. And then we could do the math here. And 2/3 times 132 is going to be 88, and then plus 8. And this is 96, and this will be inches. In our last example, we look at making linear models involving speed. John and Mary are driving westward along I-76 at constant speeds. The graphs in the figure below here show the distance in miles that they have traveled from Philadelphia at a time in X hours, where X equals 0 corresponds to noon. Note that at noon, John has already traveled 150 miles. So you can see that on the graph down here. When X equals 0, John is already at 150, whereas Mary is still in Philadelphia, right? Mary has not traveled anywhere yet at noon. So in the first part of the question, at what speeds are John and Mary traveling? Who is traveling faster? And how does this show up in the graph? Well, to find out their speeds, we need to find out the rate of change. And that is nothing more than the slope. So for John, the slope of his line is going to be, using the slope formula, we've got to take this point here, which is the point 4,350, and this point down here, which is the point 2,250. And if we use the slope formula, we have 350 minus 250 divided by 4 minus 2. And this is going to be 50. And we are measuring the distance in miles and the time in hours. And so this will be 50 miles per hour. And so that is John's speed. Now for Mary, same idea. The slope of the line for Mary is going to be, take these 2 points and use the slope formula. So this point here is the point 150. And this point over here is the point 300. And so her slope will be 300 minus 150 divided by 4 minus 2. And this is 150 divided by 2, which is 75. And again, this is miles per hour. So Mary is driving quite a bit faster than John. Next, it says find functions that model the distances that John and Mary have traveled. So we'll just continue this over here. For the second part here, we want to find functions that model the distances that John and Mary have traveled as functions of x. So the distance is the variable y, and the time is the variable x. And we know that for John, the slope of his line is 50, and the y-intercept is 150. So for John, the equation must be y equals 50x plus 150. And for Mary, the slope of her line is 75, but the y-intercept is 0. So her distance traveled is simply going to be y equals 75x plus 0, which is just 75x. Now for the next part, how far will John and Mary have traveled at 5 p.m.? So let's keep in mind that 5 p.m. corresponds to x equals 5, right? Because 0 is noon, so 5 hours later would be 5 p.m. If we plug in x equals 5 for John, we're going to have y equals 50 times 5 plus 150, and this is equal to 400. So after 5 hours, John has traveled 400 miles, and that's where he'll be at 5 p.m. For Mary, her distance traveled is simply 75 times 5, and 75 times 5 is 375 miles. Now for the last part of this problem, it says, for what time period is Mary behind John? Will Mary overtake John? And if so, at what time? Well, if you look at these lines, it does appear that Mary is going to overtake John because the slope of this line is steeper than the slope of this line. So you can see that if you extended these lines outward a little bit, right, you can see that it does appear that Mary is going to overtake John at some point. So what we need to do is find out, when will the distances travel be equal? When does this happen? Well, the distance is y. So if the distance here is 50x plus 150, and the distance here is 75x, we just need to set these two expressions equal to each other. So 50x plus 150 is equal to 75x. Subtracting 50x from both sides, and then dividing by 25, we see that x is equal to 6. So will Mary overtake John? The answer to that question is yes. At what time will this happen? It will happen at 6 p.m. And then for what time period is Mary behind John? From noon to 6 p.m., Mary is behind John. And that concludes this video lesson.